So if you were just randomly going through the never-ending list of Pythagorean triplets, one thing you might notice is that a Pythagorean triplet always contains at least one multiple of 3. So if I make a right angle triangle over here, let's say this is 5, then this is 3 and this is 4, here's your multiple of 3. If I make another right angle triangle, which this app doesn't recognize, okay, there, okay. Finally, so let's say there's another right angle triangle. If this is 13, then this is 12, this is 5. Right, so the Pythagorean theorem says that a squared plus b squared will give you c squared. So let's try to look at things in terms of multiples of 3 and what happens when you square them. And by the way, the proof is much shorter if I use modular arithmetic notation, but since some of you might not be familiar with it, let's not do that. So if something is a multiple of 3, right, when I square it, it will still remain a multiple of 3. In other words, if a number leaves a remainder of 0, then after squaring it, it will still give a remainder of 0, right? Pretty basic. If a number is one more than a multiple of 3, in other words, if it leaves a remainder of 1, then it is 9n squared plus 3n plus 1. This portion is a multiple of 3 plus a 1, so it still leaves a remainder of 1. Right, but things change if you look at a remainder of 2. So if something leaves a remainder of 2, after you square it, it will be 9n squared plus 12n plus 4, which can be written as 9n squared plus 12n plus 3 plus 1. Right, so this much a multiple of 3 plus a 1. So if something leaves a remainder of 2, after you square it, it leaves a remainder of 1. So we come to the conclusion that if x is an integer, then x squared will leave a remainder of either 0 or it will leave a remainder of 1. Right, so if c is a whole number, then c squared will leave either a remainder of 0 or a remainder of 1, and we know that c squared is a squared plus b squared. So a squared plus b squared will give a remainder of 0 or a remainder of 1. Now, the case of remainder of 0 is pretty easy. C will only give a remainder of 0 when both a squared gives a remainder of 0 and b squared gives a remainder of 0. Right, so if both a and b are multiples of 3, then c squared will also be a multiple of 3. Right. The point I'm getting here at is, if let's say x is y plus z, right, and y is, let's say, 3n plus ay and z is 3n plus az, then x will be 3n plus ay plus az. In other words, if you are looking at remainders and you know that these two are added, then the remainder of x will just be these two remainders added together. Right, so when we're talking about the case of r being 0, both of a squared and b squared will give r equals 0. Right, the case where c squared gives a remainder of 1 would be when a squared gives a remainder of 1 and b squared gives a remainder of 0, or vice versa. Right, just noting the fact that one of them will give a remainder of 0 and the other one will give a remainder of 1. And so we see that these two are the only cases. What cannot happen is that a squared gives a remainder of 1 and b squared also gives a remainder of 1, because then this would imply that c squared gives a remainder of 2, which cannot happen because c is an integer. Right, that would be a contradiction. And we are done, because in this case we have one multiple of 3, in this case we have two multiples of 3. In both the cases, we have the situation that in a Pythagorean triplet you have at least one multiple of 3, and QED.